For this lecture, we're going to focus on categorical predictor variables and the use of transformations. In the regression examples we have done so far, simple and multiple, the x variables used took on a range of numerical values, such as the size of the house. Now let's consider how to enter a categorical variable into the model. Example, does a house have brick or not? The answer is easy in terms of how we do that. We will create what is called an indicator variable, or sometimes called a dummy variable, which is simply 0 for no and 1 for yes. Consider this application in which we have information on the salaries of employees along with the gender and the number of years at the company denoted as experience. First question we could ask, is there a gender effect in terms of salary? Here we have a box plot of salary against the gender, and we can see that the box plot for the female employees seems to be displaced lower than the male employees. If we look at the difference in means, the average male employee salary minus the average female employee salary is 8.2955, around $8,300. So there seems to be something going on. Let's investigate further. Let's bring this application into a regression setting. Let's start out with a simple regression of salary only on a 0-1 male variable. What is the interpretation of beta 1? Now let's not worry about the error term. On average, the errors equals 0, so that means the betas reflect on average, in this case, the salary differences between male and female. When we substitute in 0 for male, we get the average salary for females to be beta 0 because this term just goes away. When we substitute in 1, we get beta 0 plus beta 1, which would be the average salary for males. So beta 0 reflects the baseline, the salaries on average for females, and beta 1 reflects the difference in salaries between male and females. How can we create these 0-1 variables? Well, there are a couple ways. If you have the add-in, you can go to add-in and then choose make dummy variable, highlight gender, click OK. When you do that, you will see two columns created called gender female, gender male, and they are 0-1 indicator variables, and you can see indeed they are correct. For example, in the first row, the individual is male, so female indicator variable is 0, male indicator variable is 1. You can rename these columns as straight up female and male just to make the names shorter. You can actually make the indicator variables without the add-in, and the way to do that is to highlight, in this case, the gender column, and then go to columns, pull down. From there, go to utilities, and then make indicator columns. After doing that, you will see that this approach also creates two columns, which are the dummy variables for female and male, the same values as we had earlier. Either way works. I'm now going to fit a regression of salary on the male indicator variable. We get a regression output showing an intercept of 47.209929. and a coefficient for the male variable of 8.2955126. So if we want to make predictions of the salaries for males versus females, we simply substitute in the 1 and 0, and we see the values of 55.505 and 47.209. I want you to recognize these are the y-bar values that we had on an earlier slide, and the difference between these two values is 8.2955, which was what we found when we took the difference of the averages. So the indicator variable regression subsumes the average comparisons that we did earlier. And we're concluding from the regression that on average it is estimated that a male makes about 8,300 more than a female in the company. Now, is this a potential discrimination case, a court case? At this stage, it would be very premature because we haven't taken into account other variables such as experience, education, and many other variables. I'm now going to go to Graph Builder and make a scatter plot of salary against experience. I dropped the gender variable in the overlay box to color code males versus females, and we can see here that the male data in red are generally above the female data in blue. Now we did a regression only on the indicator variable, which gives us two predicted values, namely 47.209 for the female group and adding 8.2955 to the 47 for the male group. So from the perspective of the scatter plot, our fitted models are only two horizontal lines. We're not taking advantage of the experience data. Let's add experience to the mix. Now we have a multiple regression on male and experience. If we make substitutions for the male variable of 0 for females and 1 for males, we get the following breakdown. The mean salary for females equals beta 0 plus beta 2 times experience, and the mean salary for males is beta 0 plus beta 1, which I've grouped together in the intercept, plus the beta 2 times experience. Again, beta 0 reflects the baseline. It's the baseline salary when experience is 0, and beta 0 plus beta 1 reflects the salary differential between males and females for a given level of experience. Here we see the regression on male and experience, and we see the coefficients. We see the coefficients of 8.0118, which is around 8,000 more for males relative to females, not any better than what we saw earlier. We have an adjustment with the experience variable in the model that's saying basically for every years of experience, there's about 0.98 or about $1,000 more salary on average. If we make a substitution of 0 and 1 for the male variable, we can find two basic lines resulting, one for the male employees and one for the female employees. They are lines of same slope because the coefficient in front of experience is the same, but different intercepts reflecting the displacement from female to male of that approximately $8,000 shift in salary. And that amount, that shift, is the same amount added across the board regardless of the level of experience, which gives us two parallel lines. Now, does it seem like two parallel fitted lines are appropriate for the data? I'm going to suggest maybe not. If we look at the red points, they seem to have a greater slope than the blue points. So we'll want to figure out how to model that. Before we figure out how to model a scatter plot with two different slopes, let's talk about having more than two categories. In the gender example, we have two categories, male and female, and we only needed one indicator variable because with the one indicator variable, we can figure out whether the individual is male or female just by virtue of the values being 0 or 1. In general, if we have J categories, then we need at most J minus 1 indicator variables. Let's consider the house prices example where we have a variable called neighborhood, and there are 3 neighborhoods, east, north, and west. How do we model that? Well, we create 3 indicator variables here for each of the neighborhoods. Now let's add the neighborhood information to the model on top of square footage. Notice that I only use 2 of the 3 indicator variables because if we know 2, we know the third. So this is the notion that if you have J categories, you only need at most J minus 1 indicator variables. Here we have 3 categories. We only need 3 minus 1 indicator variables. I happen to choose east and north. What's the interpretation of all these coefficients? Well, we can go through the substitution. For a house in the west neighborhood, east and north have the values 0. So all we're left with is beta 0 plus beta 1 times square footage. Thus, beta 0 reflects the baseline of homes in the west neighborhood. For the east neighborhood, we put a 1 for east and 0 for north. So we pick up the beta 2, as you can see here in the intercept. So beta 2 is the difference between selling prices of homes in the east neighborhood relative to the west neighborhood for a given square footage. And then finally, beta 3 would be the difference between homes selling in the north neighborhood relative to the west neighborhood for a given square footage. Here is the fitted model based on the noted X variables. Let's take the multiple regression shown on the previous slide and break it down. For a house in the west neighborhood, we would stick in 0 for east, 0 for north, and we get 62.776 plus the 46,385 times square footage. For an east home, we would stick in 1 for east and 0 for north. That minus 30.9666 would come off the intercept value to give us 31.809871 plus the square footage term. And then finally for north, we would subtract off the minus 41.53531 off the intercept to get this value of 21.241171. So we have 3 lines here with same slopes vis-a-vis the square footage. We can also see that west homes on average sell more for a given square footage than east homes, and east homes sell more than north homes. As noted, breaking down the fitted models by neighborhoods gives us 3 parallel fitted lines, as we see here on the slide. And we see that the fitted models are well placed in terms of the 3 color-coded scatters. Now, I will note that in JUMP, you don't have to turn the categorical variables into 0, 1 variables. You can actually give that original nominal variable straight into the regression platform. Now, I'm going to advise you not to do that, but I want to actually show you that you can so that I can emphasize that you shouldn't. You see here in the fit model platform, I gave square footage and neighborhood. That's the original nominal variable. Here is the regression output when we regress on the nominal variable rather than creating the 0, 1 indicator variables. We get an equation. This equation includes square footage and a couple factors here of east and north. Let's show you how to make predictions off of this multiple regression. For the east neighborhood, we would put a 1 in for the east variable and a 0 for north. Here you can see the 1 for the east. I'm not showing the north one because 0 just cancels out that coefficient, and we get the following line. For the north neighborhood, we indeed put a 1 for north and 0 for east, and we get the following line. So far, so good. But here is where it gets a little different. For the west neighborhood, which is not in the model, what we do is substitute in -1 for all the variables or factors that are in the model. And we get the following line. If you compare these three lines with the previous slide, you will find that they're exactly the same as when we did the 0-1 approach. So algebraically, all these things are the same. The problem is that interpreting the coefficients here based on this 0-1 -1 coding is not straightforward. It's not so obvious. Also, you'll find out if you were to do it, and I don't want you to do it, when we get to model selection and do things like stepwise regression, which you'll understand later, by putting in the nominal variable, we get these really hard to understand output. Whereas if we do indicator variables, simply 0 and 1, things are easy to understand. So for this class, I do not want you to regress or use the original nominal variable in a regression setting. You must create the 0-1 indicator variables and go from there. Let's return to the salary example. I hinted earlier that parallel lines might not be accommodating the nature of the two scatters of male versus female that seem to be sloping with different slopes. To have different slopes for the different sexes, we're going to add what's called an interaction term, or sometimes called a multiplicative term. Here you can see it. I'm going to have male as we originally had, experience as we originally had, but I'm going to add another variable, which is the multiplication of male times experience. Let's see what this does. Let's substitute the 0 and 1 values into male. For the female group, we'll put a 0 here for male and a 0 here for male. So what we'll have is beta 0, the second term will go away, plus beta 2 times experience, and this third term will go away because of the 0, and we have here beta 0 plus beta 2 times experience. For the male group, we have beta 0 plus beta 1 times 1, and you can see that below here as the intercept, plus beta 2 times experience, plus beta 3 times 1 times experience. So we'll have beta 2 times experience plus beta 3 times experience. We can pull out the experience variable and see that the coefficient in front of experience is now beta 2 plus beta 3. So we have two different lines with different intercepts and different slopes. Mission accomplished. We want to make the interaction variable. One way to do so is to right-click on the next available empty column and pick New Columns option. We can then name the new column. Here I'm calling it male times experience. Then at this point, we open up column properties that you can see right here and pick formula. Now, sometimes it may come back and say edit formula. Either way, you'll get to the formula platform. Here you can see the formula platform, and I'm going to click the multiplication sign, and then I will click in the column which is male and the column which is experience to make the multiplication between those two columns, and then I will click OK. After that, we will find a column which I named male times experience, but the rows indeed are the multiplication of the male column times the experience column. For example, 1 times 2 in row 1 equals 2. The next row is 0 times 13 is 0, and so on. This is what I want to introduce to my regression. So here you go. Here is a regression on male experience and male times experience, and you can see all the estimated coefficients. Here we see again the multiple regression equation. Let's break down this equation into the two groups. For females, we'll put a 0 for male. So I'm putting a 0 here, a 0 here, and we get a line of 44.808 plus 0.2799 times experience. For the male group, I'm going to put a 1 here for male, a 1 here for male, and collect all the terms together, and I get 41.957789 plus 1.5277618. You see two different lines with different intercepts and different slopes. Here is a superimposing of those two lines on the scatter plot where I color code male versus female. The lines seem to do a really good job in getting into the distinct scatters. In a sense, the company is looking worse because the gap between male and female is getting wider with more years of experience. Now, that's what an interaction effect can get at. When we only had an indicator variable, the difference between, let's say, female in blue and male in red was the same regardless of experience, and thus we got two parallel lines. That's not the case here. With more years of experience, the difference between male and female employees is getting greater and greater. Now, my previous slide is showing a concerning issue between male employees and female employees. I don't think we're ready to go to court on this because we really have to make sure there's no omitted variable bias. We're not missing out on other variables that need to adjust for the salary difference. For example, education level, job categories. But my example of studying salaries by gender is not academic, nor studying, for example, racial background or ethnic background is not an academic exercise. Statistical analysis, including the use of multiple regression, is commonly used in legal cases, as seen from the excerpt below from a case log. If you look here, the introduction talks about the use of multiple linear regression analysis in litigation. It also talks about using regression analysis to filter out, that means to control for several legitimate factors such as education and experience, so then one can focus on discrimination as a possible situation at hand. So realize that potentially a company's database can be analyzed, and they have been analyzed in court cases for teasing out any inappropriate behavior by the company, whether in terms of discrimination or any other inappropriate behaviors. Let's switch gears here and talk about transformations. In simple and multiple regression, we emphasize the importance of performing residual analysis, that is, diagnostics. We're performing these diagnostics to check if assumptions like linearity is at hand, whether the assumption of normality for the errors is reasonable, whether the assumption of constant variance of the errors is reasonable. Not all data are linear. We could have nonlinear patterns. One remedy might be to transform the data with something like the log transformation. With this example, I'm actually going to add a squared term to give us a quadratic regression. The data we will look at are from a sample of the 2000 US Census y-axis. In particular, we have the median wage rates versus age for each of the genders. Here are the scatter plots of the median wages versus ages for each of the genders, and clearly the data are exhibiting nonlinear patterns. If I were to ignore the nonlinearity in the scatter plots and fit lines to each of the scatter plots, the residuals will reflect the curvature that we failed to model by showing pattern to the residuals with curvature, as you can see here. Now, the histograms are meaningless to look at since the data are not random. Histograms are only meaningful for understanding the distribution of random data. At this stage, our residuals are not random. We would ignore the histograms. Let's consider a model that goes beyond a line of only having age and adding age squared. That's simply done by highlighting the age column, then going to new formula column, then transform, then square. When you do that, you'll see that JMP will automatically create a column of squared values, in this case of age squared values. I fit the male wage rate data and the female wage rate data to the age and age squared variables. We get two different regression equation output, both quadratic functions. And if we look at the residuals from each of these fits, they look much more random. Thus, it seems like we've captured the curvature in the data. Here I plotted the fitted models for both of the genders. Notice how nicely the quadratic models capture the curvatures. Visually, we see that the wage gap grows between genders for older and older ages. That's obviously a concerning gender inequity at hand in our country. Second, we notice that the female wage rate tops out at an earlier age than the male wage rate. Now, I'll have you sort of pontificate on why that may be the case. But in the end, this is a great example to show you how to fit quadratic models. For the wage rate data, we found that the quadratic fit seems to be more than sufficient for capturing the curvature. We could add more terms to the polynomial like x cubed and so on. This would add more bends and turns, but I'll tell you, in most applications, a quadratic polynomial is more than sufficient. But we could always add more terms depending on the application. Let's take a look at another example. Here I have 397 cars, and we have on the y-axis what we're trying to predict is miles per gallon, and the x variable denoted by the letter D refers to displacement. In automobile talk, this refers to the total volume of the cylinders that the pistons sweep during a stroke. It is the maximum amount of air an engine can displace. We see that there is indeed a negative relationship between miles per gallon and displacement, and we see curvature to the data. Given the curvature in the scatter plot, I fit the data with a quadratic model. In particular, I created a d squared term and ran a multiple regression on d and d squared. Here is a superimposing of the predicted values on the scatter plot. You can see that the fitted model is starting to curl up, and that doesn't make sense to this scatter plot that eventually miles per gallon will start increasing. And the curling up is not a shock to us because a quadratic, after all, is a parabola, and it eventually will start curling back up. Remember the math review discussion where we showed you general quadratic functions. Now, how can we model curvature without having curling back up? One way is to not use d squared, but use 1 over d. Let me show you what I mean. Let me show you how to create 1 over d. Now remember, d is the x variable, so I'm creating in general 1 over x. What I do is I highlight the d column, then I go to new formula column. You can't see it here, but then I go to transform and then to reciprocal. This will give us a new column, indeed 1 over d. Here's the multiple regression fit on d and 1 over d. You can see the predicted values indeed get at the curvature. This curve will not curl back up as the quadratic does. What you will recognize is that when we move into larger values for d, that is, we move to the right here, this 1 over d term will go to 0. It'll just wash out, and we'll be left with only a linear relationship. So the implication is, as we move to the right, the function will eventually just continually go down, dictated by basically this linear function. Suppose your understanding of the application suggests that the y values should not continually go down, as is the case with the previous fit of having d and 1 over d in the regression model, and that your understanding of the y behavior is that it will eventually flatten out to some level. How could we model that? Well, we don't include the d term. We only include, in this case, the 1 over d term. Now, again, this 1 over d term will go away when d becomes big, but you're only going to be left with this constant value. That means this curve here will eventually flatten out to a horizontal line at 10.199859. So I've given you some examples of how to fit curvatures of different sorts. Hopefully this is helpful. It's not only fitting the data as best you can, but it's also understanding the context and the nature of the application. I have talked about the importance of checking residuals for constant variance because the regression model assumes constant variance across the x values. With a single constant variance, we have a single estimate in MSE. From the direct marketing application we studied in a previous lecture, here is a plot of amount spent by customer against his or her salary. Notice the scatter plot is showing a clear funneling pattern, as do the residuals from the fit. Take a look at the prediction intervals superimposed on the scatter plot on the left here. We see the prediction intervals upper and lower, and because we're assuming constant variance, the prediction intervals are too wide over here on the left side for smaller values of x and too narrow over here on the right side for larger values of x. This, of course, is problematic. Since MSE is embedded in the standard errors of estimates, non-constant variance can undermine hypothesis testing, be it t-tests or f-tests. Now, there are a number of ways of dealing with non-constant variance, and we're not going to be able to touch on the many ways to deal with the problem. I'm only going to look at one of the most popular approaches that often works in application, is to transform the y or x or both variables with a common class of transformations called the power transformations. The power transformations involve raising the x or the y or both to some power lambda. For example, if lambda equals 0.5, this is the equivalent of taking the square root of the data. Now, if you have some negative numbers in the data, you can't take the square root, so you might have to add some constant to make all the observations positive. It turns out that as lambda approaches 0, this power transformation actually approaches the natural log. which is extremely interesting. We can't prove that. You'll just have to take that at faith. Finally, I should note that these transformations are not only useful for dealing with variance problems, but also can turn nonlinear situations into linear situations. And also they can remedy non-normality that might be seen in the residuals. Often if we see positive skewness in the residuals, we might want to take a transformation of the y variable, and that might actually help ultimately the residuals being more closer to the normal distribution. Here are some popular choices for lambda for dealing with non-constant variance or positively skewed data. A trial and error approach can typically converge to a reasonable choice quickly. Raising the data to lambda equaling 1 is the innocuous no transformation, so we want to move away from 1, and typically we'll go in the direction of less than 1, for example, taking the square root, which is lambda equaling 0.5, or taking the cube root, or taking the fourth root, or the fifth root. As you can see, we eventually will converge on lambda of 0, which is the log transformation, and we can go to the other side of 0 to, for example, -1, which would be taking the inverse of the variable. Now, the log transformation actually turns out to be one of the most common remedies in business and economic applications. If you think about the funneling in the direct marketing example, what is funneling? We have on the low end of X and Y the values tightly bound together, and as we move to larger X's and larger Y's, they start spreading out. So it would seem that we would want to transform both the X and the Y. I'm going to take the natural log of both variables. By now we should know how to do that. We highlight the salary and spent variables, go to new formula column, then transform, then log. Here's a screenshot of the direct marketing data table. We can see here that we have log salary and log spent. Let's now look at a plot of log Y versus log X, in particular log spent versus log salary. And notice we have now a scatter plot with more even dispersion going from left to right. So we have tamed down the funneling and we can proceed with standard regression fitting. As you can see here, I'm going to the fit model platform. I'm going to regress log spent on log salary. Here's the fitted model. You can see the superimposing of the line of the scatter of log spent versus log salary. And here are the residuals plotted, namely residuals against predicted values, and you can no longer see that funneling. It's basically constant in variance. It's not perfect, but it's a lot better. What I can do now is save the predicted values, which are predictions in logged units, and save the individual confidence interval, which are the prediction limits in logged units. We can then convert back these logged units to original units by highlighting them and do new formula column transform exponentiation. Here you can see I'm doing it on the predicted values by highlighting new formula column, transform, exponentiation, and here are the predictions in original dollars. You would do the same thing on the lower and upper prediction limits. Now look at the scatter plot in original units along with the prediction limits that we took from log back to original units. Notice the prediction limits are very well positioned in contrast to the original prediction limits. They are following indeed the funneling very nicely. This is a beautiful looking picture. So hopefully this example has demonstrated the importance of addressing violations in regression assumptions to get a better model summary for the data. Since we will so commonly log data, it's useful to talk about the interpretation of regressions based on logged variables. Recall the change in natural logs is approximately the percentage change in decimal value. So if we have y1 equaling 15, y2 equaling 16, the standard computation would be 16 minus 15 over 15, and that would be 0.067. But if you took the difference in natural logs, it's essentially the same value as you can see here. So that means if I multiply this by 100, I would have it in percentage terms. In general, 100 times the change in logged y's equals the percentage change in y. And I'm going to denote that by 100 delta log y instead of having to write this whole thing each time. 100 times delta log x is a percentage change in x. Let's consider the case where we don't log, just the standard case. What's the interpretation of beta 1? It's the change in y over the change in x. If I rearrange this, we can have it as the change of y equals beta 1 times the change of x. That means if the change of x is equal to 1, then the change in y is equal to beta 1. Here's a summary. 1 unit change in x is associated with a beta 1 unit change in y. Let's consider the case where we don't log the y, but we log the x. So beta 1 would be the change in y over the change in logged x. I'll divide both sides by 100, as you can see here, so the bottom here becomes the percentage change in x. I'll take this fraction relative to this leftmost fraction, rearrange things, and you should be able to see in the end we have for a 1% change in x, we have a beta 1 over 100 unit change in y. So it's unit change to percent change. What about logging the y but not the x? We can go through the same game. The beta 1 would be the change in log y over the change in x. I'll multiply by 100. This will give the top part here being percentage change in y over change in x, and we have 100 beta 1 over here. Rearrange things, and we should be able to see in the end that what we have here is for a 1 unit change in x, we get 100 times beta 1 percent change in y. So this is percent to units. This measure is referred to in economics as semi-elasticity. Finally, let's consider the logging of y and the logging of x. So you have beta 1 as a change in log y over the change in log x. We'll multiply the top and bottom by 100. This gives us percentage change in y over percentage change in x equaling beta 1. Rearrange things. You should be able to see that what we have is for a 1% change in x, we get a beta 1% change in y. So this is percent to percent, and this is the well-known concept in economics of elasticity. Let's look at another example to demonstrate the usefulness of transformations. The data are for 50 states and the District of Columbia. We have n equaling 51. The y variable here is fuel consumption per capita. The x variable is the population density defined as population divided by land area. From the left scatter plot, we don't see much of anything. There's not a lot to be desired here, but we recognize that the smaller x values are packed together and they progressively spread out as we move to the right. This suggests we might only need to transform the x values. The right scatter plot is a plot of the y variable against logged density. we can now see the transformation brought out the pattern in the data. We have a really nice negative relationship, which is suited for fitting a line, which was not seen in the left scatter plot. So this is quite neat. Does a negative relationship make sense? It sure does. Regions with small density, for example, areas like Wyoming or Alaska, you're going to have much greater fuel consumption because folks will have to drive far distances, let's say to go shopping or go to various areas in the state. Whereas in high density areas, you might have public transportation. So you can think this out. It really does make sense. Here's the regression fit, and you can see that the linear fit is a nice fit to the data as reflected by the residuals. And we see the estimated coefficient in front of log density is minus 24.53. Let's round out this lecture with the interpretations of the coefficients that involved logs. For the direct marketing, we had a log-on-log regression, and we found B1 to be 1.02, which is an elasticity measure. So that means for a 1% increase in salary, which could mean going from 40,000 to 40,400, or from 100,000 to 101,000, there's an expected 1.02% increase in spending amount. For the fuel consumption application, where we did not log the Y, but we logged the X, we found that B1 equals minus 24.53. So going back to our discussion of Y on log X, this would mean that for a 1% increase in density, there's an expected minus 24.53 over 100, or minus 0.245 decrease in per capita fuel consumption. That's about a quarter of a gallon decrease. Okay, that is our lecture on categorical variables, some ways to deal with nonlinearities, and the use of transformations for variance stabilization. I hope you enjoyed it. Talk to you next time.